these are your notes for Unit 4, Day 5 of Pre-Calculus. If you would like to see the warm-up, your review question, or any homework questions we covered in class today, just look at the finished notes. So today we're going to talk about polynomials and some things that go with polynomials when we divide them. So we're going to talk about the remainder and factor theorems. We're going to review long division and synthetic division. We'll be able to find zeros of a polynomial function algebraically and on a graph. And we'll use that idea to solve polynomial equations. And then we're going to talk about the intermediate value theorem. So a review of long division. So polynomial long division, you want to make sure that the first guy goes underneath the house and that it's not missing any terms. So we have a p to the third, we have a p squared, we have a p, and we have a constant. So he's not missing any terms, so I just get to put him in. So p to the third minus 10p squared plus 20p plus 26, and then we're going to divide by p minus 5. And again, you don't want that to be missing any terms. So then you think, just like normal long division, p times what would give me p to the third? Well, I need a p squared, and then you take that and you multiply it by the terms on the outside. So p squared times p is p to the third, and p squared times negative 5 is negative 5p squared. And just like within normal long division, now you subtract. And so p to the third minus p to the third is 0. Negative 10p squared minus negative 5p squared is negative 5p squared. And then you bring down the next term, just like you would in normal long division. So then you do the same thing. Guy on the outside, so p times what is negative 5p squared? Well, that's going to be negative 5p. And then multiply that out. So negative 5p times p is negative 5p squared. Negative 5p times negative 5 is positive 25p. And then again, we're going to subtract and subtract. So the 5p squareds go away. 20p minus 25p is negative 5p. And then bring down the 26. And then p times what is negative 5p? And that's going to be negative 5. So we get negative 5p and then plus 25. And then subtract, subtract. My remainder is 1. So that's my remainder. The remainder always goes over what you were dividing by. So the remainder is positive, so plus 1. And then I was dividing by p minus 5. So my remainder is going to be 1 over p minus 5. And so my answer to this long division problem is p to the second minus 5p minus 5 plus 1 over p minus 5. Let's try the next one. So it's top divided by bottom, but notice this one doesn't have any x squared, so I need to put in a 0x squared, or it's going to look uglier when I try and divide. So 3x to the third plus 0x squared plus 4x plus 11, and then divided by x squared minus 3x plus 2. That wasn't missing any terms, so I don't need to put zeros in. X squared times what is 3x to the third? Well, that would be 3x, and then if I multiply that out, I get 3x to the third minus 9x plus 6x, and then subtract, 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 and this would be 9x squared minus 2x, and then bring down the next term, plus 11. And then x squared times what is going to give me the 9x squared? Well, that's going to be plus 9. So then multiply that out. That would be 9x squared minus 27x plus 18. And then subtract, subtract, subtract. And then this would be 25x minus 7. And this is my remainder. And then remember, you always put the remainder over what you were dividing by. So plus 25x minus 7 over x squared minus 3x plus 2. And then that would be my answer to that long division problem. So that's long division. You have to use long division if you are dividing by a trinomial or non-linear binomial. So if you're dividing by anything that's bigger than a binomial, and if the binomial is non-linear, meaning it has an x to the square, x squared or x cubed in it, then you're going to have to use long division. If you are just dividing by, so if you are dividing by a linear binomial, then you can use synthetic division. So synthetic division, you would take the term that you're dividing by. So in this problem, we're dividing by p minus 5. You would take the p minus 5, set it equal to 0, and you get p equals 5. That's the number that's going to go in what I call the house. I don't know what it's actually called, so I'm going to take that 5 and put it in the house. And then we started with the p to the third. So we have a p to the third, p squared, p, and then you're going to have a constant. And then you list out the coefficients. So this row right here are going to be the coefficients of those in the problem. So I have 1p cubed, I have negative 10p squared, I have 20p, and then 26 is my constant. And then you leave a space. And then the first term just drops down. So I'm going to drop down that 1. And then you take that number and you multiply it by the house number. So 1 times 5 is 5. That 5 is going to go in the next column. So it's going to go underneath the negative 10. For this, we add going down. So we're going to add all the columns in synthetic division. So negative 10 plus 5 is negative 5. And then we're going to take that number and multiply it by the house. Negative 5 times 5 is negative 25. And then again, we're going to add going down. So that's going to be negative 5. And then multiply by the house number. Negative 5 times 5 is negative 25. And 26 plus 5 is 1. That last number, the very last number you get, is going to be the remainder. So technically, I was dividing by p. So since I'm dividing by p, all of my original guys are going to drop by 1. So this is going to represent a p squared. That's going to represent the p. That represents the constant. And there's my remainder. So this is going to be 1p squared minus 5p minus 5 plus 1 over what I was dividing by, and I was dividing by p minus 5. We did this problem up here, and notice we get the exact same thing that we got with long division, p squared minus 5p minus 5 plus 1 over p minus 5. So on the next one, we have x to the third plus 4x squared minus 5x. Notice we're missing an x term, so we got to plug in a 0x. And so we're dividing by x plus 3, so set that equal to 0, and you get x equals negative 3. That's the number that's going to go in the house. And then we have an x to the third, x squared, x, and a constant. So we have 2, 4, 0, and negative 5. Bring down the first term, then multiply by the house, and you get negative 6. And then you add going down, so negative 2, and then 6, and then 6, then negative 18, and then negative 23 should be my remainder. I started with x to the third, but I divided by an x term, so that'll be x squared, x, my constant, and my remainder. So this will be 2x squared minus 2x plus 6, and then minus 23 over x plus 3. So that's a review of long division and synthetic division. So now using that idea, we have something called the remainder theorem. So for instance, if we want to find the remainder when x to the third minus 5x squared minus 5 is divided by these terms, notice it's missing a 0x. So if I'm going to divide it by x minus 3, 3 gets to go in the house, and then I have x to the third, x squared, x, and my constant. So I would have 1, negative 4, 0, and negative 5. Bring down the 1. And so then I would have 3, negative 1, negative 3, 9, and then my remainder is 4. Well, watch what happens if I found f at 3. So if I plug 3 into this original function, let's see what happens. I would get 3 to the third minus 4 times 3 squared minus 5. So I would get 27 minus 36 minus 5. Did I do this right? So x to the third minus 4x squared plus 0x minus 5. So 1, 3, negative 1, negative 3, negative 3, negative 9. There we go. And then this would be negative 14. So my remainder was wrong. And then this is going to work now. Sorry about that, guys. So negative 5 minus 9 is negative 14. So my remainder is negative 14. And so now if I found f at 3, so I plug 3 into all of those x's, I get 27 minus 36, which is negative 9, and negative 9 minus 5 is negative 14. Notice f at 3 and the remainder are the same thing. Let's see if it works if I try x plus 2. So if I take negative 2 and do the exact same thing, x to the third, x squared, x and my constant, I would get 1, negative 4, 0, negative 5. So bring down the first one. So 1, negative 2, negative 6, 12, 12, negative 24, so negative 29. So my remainder is negative 29. Let's see what happens if I find f at negative 2. So I would get negative 2 cubed minus 4 times negative 2 squared minus 5. So this would be negative 8, and that would be minus 16 and minus 5. Well, that's negative 29. So if you want to figure out what f at 3 or f at negative 2 is, you can also use synthetic division and figure out what the remainder is, and they'd be the same thing. If we want a specific polynomial to be a factor of a polynomial, then we need the remainder to be 0 when we divide. So if we want it to be a factor, meaning if you were to factor something, put it in parentheses, and you want a specific polynomial, binomial, trinomial to be a factor, then when you divide them out, you want the remainder to be 0. So if you think about 12, the factors of 12 could be 3 and 4. When I take 12 divided by 3 or 12 divided by 4, I get a remainder of 0. The same thing is true for polynomials. You want the remainder to be 0 if it's a polynomial. So if I want to know, is x minus 1 a factor of this? Meaning if I tried to factor this into its factors, would x minus 1 be a factor? Well, we would divide it out, and we would want the remainder to be 0. So I have 2x cubed minus 1x squared plus 2x minus 3. So bring down the first term. So this would be 2, 2, 1, 1, add going down 3, 3, 0. So yes, x minus 1 is a factor. So x minus 1 is going to be a factor. Is x plus 2 a factor? Well, let's take negative 2 and put it in the house. And so negative 2, and then I've got 2x cubed minus 1x squared plus 2x minus 3. Bring down the first one, so it would be 2, and then negative 4, and then negative 5, and then 10, and then 12, and negative 24, negative 27. So no, x plus 2 is not a factor. So again, if you want something to be a factor of a polynomial, then when you divide it out, you want 0 as the remainder. The Descartes rule of signs, we're not going to really use in this class, but just so you guys know and have seen it before, if you have a polynomial that's written in standard form, so like f of x equals 5x to the 4th minus 3x cubed plus 2x squared plus x minus 1. The number of positive real zeros, so if I were to solve this, so like set it equal to 0 and solve, either equals the number of variations in the sign of the non-zero coefficients, so we have a positive, we have a negative coefficient, we have a positive coefficient, we have a positive coefficient, or else equals that number less than an even integer. The number of negative real zeros either equals the number of variations in the sign of the non-zero coefficients of negative f of x. So if I tried f of negative x, I would get 5 times negative x to the 4th minus 3 times negative x cubed plus 2 times negative x squared plus negative x minus 1. Or it's that less minus an even integer. So notice how many sign changes did we have on this first one? We had 1 sign change, 2 sign changes. Well, that's it. So this had 2 sign changes. So it could have 2 positive real zeros. So like its zeros could be 3 and 2 or 5 or 6. So, or less an even integer. Or it could have 0. So it could have 2 positive zeros or 0 positive zeros. And then on the next one, if I plug in negative x, I would still have 5x to the 4th, and then I would have positive 3x cubed, and then I would have positive 2x squared, and then I would have minus x and minus 1. So notice I have 1 sign change. So since I have 1 sign change, I could have 1 negative 0, and I should have 1 negative 0, because less than an even integer wouldn't work. Again, we're not going to use that, but just so you've seen it before, that's Descartes' rule of signs. So the rational root theorem, we don't really use a ton anymore since we have Desmos and other technologies that allow us to find the zeros of polynomials rather quickly. But if you wanted to use the rational root theorems, you find all the factors of the constant. So find all the factors of the constant. And you find all the factors of the leading coefficient. And then you find all of the possible ratios that would come out of those. So find all the factors of the constant, so the term without the x. So all of its factors are 1, 6, 2, and 3. And all the factors of 2 are 1 and 2. And it's plus or minus all of those, because negative 2 times negative 1 is 2, et cetera, et cetera. So it would be the constant over the leading coefficient. So So when you do this, that's what the ratio is. You're going to take all the factors of the constant. So let's start with 1. So the factors of 6 are 1, 6, 2, and 3. So let's start with 1. So I would have plus or minus 1 over each of these. So 1 and plus or minus 1 over 2. Now let's look at 6. So it would be plus or minus 6 over 1 and plus or minus 6 over 2. So again, I'm putting all of the factors of the constant over all of the factors of the leading coefficient. All right, and now let's do the next one. So 2, so plus or minus 2 over 1 and plus or minus 2 over 2. And then we'll do 3. So it would be plus or minus 3 over 1 and plus or minus 3 over 2. So those are all of the possible zeros, real zeros. So these are all the possible rational, sorry. These are all the possible rational, meaning you can write them as a fraction, zeros of f of x. Does that mean all of them work? No, but there are all of the possibilities. So if we wanted to actually go through and figure out which one of those worked, we could use synthetic division. So these were the ones that we did. So I could test, right? So I have 1 and negative 1 as possible zeros. So I would test those. So you could test using synthetic division. Again, we really don't do this anymore because Desmos does it so much faster, but let me just show you. And remember, for it to be a 0, the remainder needs to be 0. So I need the remainder to be 0 for this to work. So I would have 2x to the third, 11x squared, minus 7x minus 6. If I try 1, so I pull down the 2, I'd get 2, I'd get 13, I'd get 13, I'd get 6, I'd get 6. Notice it worked. So that means that x equals 1 is a 0 of the polynomial, which means that x minus 1 is a factor of the polynomial. Well, now that I know that 1 works, now we have a depressed equation, meaning that we went down 1 value. So now I know that this was x to the third, so this is going to be x squared, x my constant, that's my remainder. So now I have 2x squared plus 13x plus 6. Well, now if I try and solve this, this is going to give me my other zeros. So can I multiply to 12 and add to 13? Yes. So I'm going to break up that middle term into x squared plus 12x plus 1x plus 6, and then I'm going to factor by grouping. So I'm going to pull out a 2x, and I would get x plus 6, and I'm going to pull out a 1, and I get x plus 6. So I get 2x plus 1 times x plus 6 equals 0. So that means that this polynomial factors into x minus 1 that was the first factor we found, and then 2x plus 1 and x plus 6. So my other zeros are going to be negative 1/2 and negative 6. Again, could we have done that just way faster on Desmos? Absolutely. So if I graph this guy, 2x to the third plus 11x squared, oops, I need an x, minus 7x minus 6, I should have zeros at negative 6, negative 1/2, and at 1. So negative 1/2, 1, and negative 6. So it worked. So again, we can use the rational root theorem to test zeros, or we could just use Desmos to find them. So again, on this one, if we wanted to find the real zeros, we do all the factors of negative 36, so plus or minus 1, 2, 3, 4, 6, 9, 12, 18, and 36. That's a lot of them. And then all the factors of 1, so plus or minus 1. So all of my possible zeros are 1, 2, 3, 4, 5, 6, 9, 12, 18, and 36. And then I could use synthetic division to find all of them, but we're not going to do that. We're just going to use Desmos and figure out what they are. So we had x to the fifth minus 7x to the fourth plus 19x cubed minus 37x squared plus 60x and then minus 36. So notice this guy only had zeros at 1 and 3. Those are the only rational zeros of this. So x equals 1 and x equals 3. That means that all of the other ones, there should be 5 of them, All the other ones are going to be imaginary. All right, so finding the real solutions, again, we're going to use Desmos, and we just did that one. So we're going to use Desmos, and I think it's the exact same one we just did. Yeah, so our real zeros are x equals 1 and x equals 3. So our last thing for today is something called the intermediate value theorem. So the intermediate value theorem says if you have some sort of polynomial function, and you know that it's continuous, meaning that there's no holes, so there's no holes, there's no jumps, and there's no asymptotes. So the intermediate value theorem says if f of x is continuous, and you know its start height, and you know the starting height, so you know the starting y value, and you know the ending height, you know the ending y value, then every y value in between those exists on the graph. Right? So this is my starting height, and this is my ending height. So that's my starting height. That's my ending height. I know that all of the y values in between those are going to exist on the graph. So notice they exist here, 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 and then here, 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 here. So all of those y values are going to exist on the graph. So how do I know if something would have a 0? Well, if you graph something, how do you know it's going to cross the x-axis? Well, it's going to cross the x-axis if the y values go from negative to positive, right? Here, the y values are negative because they're below the x-axis, and here the y values are positive because they're above the x-axis, or your y values go from positive values to negative values. So notice my y values are positive here and negative here. As long as that happens, then I'm going to have a 0 or an x-intercept somewhere on that interval. So to test that using the intermediate value theorem, we're going to figure out what f at 1 is and f at 2 is. So this is going to be the starting height, and this is going to be the ending height. And I want those heights to change signs. So I want one to be positive and one to be negative. And if that's true, then I would have a 0 on that interval. So if I plug in 1, I would get 1 to the 5th minus 1 to the 3rd minus 1, which would be 1 minus 1 minus 1, which is negative 1. So this is negative. So that would be below the x-axis. And then if I plug in 2, I get 2 to the 5th minus 2 to the 3rd minus 1, which would be 32 minus 8 minus 1, which is 25, which is positive. So since my y values went from positive to negative, yes, there has to be an x-intercept between x equals 1 and x equals 2. And so that's how we can use the intermediate value theorem. Your homework is from 4.6. Let me know